When you start learning about motion in a class like this, you typically start with the one-dimensional motion. And the reason why it's called a one-dimensional motion is because all the objects in that particular analysis mode move along one axis. So, for instance, we might have a ball or a car, and we're analyzing how it moves, but its motion is all along a single axis like this. It might be a car driving along the road or a ball rolling or something, all along one axis, in this case the x-axis. In another mode of one-dimensional motion, you could have an object that's just moving up and down like this, like a ball falling off a building again, but it all stays along one axis. In this case, it would be the y-axis. These are all cases of one-dimensional motion. This one stays along the single x-axis. This stays along the single y-axis, one-dimensional motion. But as we move on now, we have to start talking about two-dimensional motion. And one of the defining characteristics about two-dimensional motion is the so-called launch condition. What is it that gets the object moving in the first place? And this is where the first difference will come in. Typically, we have a ground like this, and the object will be sitting here ready to go, ready to start the problem. And instead of just launching it straight horizontal for one-dimensional motion or straight vertical for one-dimensional motion that way, we're going to launch it sort of like this. In other words, the v0 vector, the initial vector, the v0, will be at some angle relative, say, to the x-axis. This is the launch condition now. So as you can see, there's two components of the motion. One is going to be this way along the x-axis. The other is going to be straight up along the y-axis. And the object will do a subsequent motion. Now, you're probably familiar with this type of motion because what the object is going to do now is it can sort of trace out a parabola like this as it goes. But that's the key to the motion. It is two-dimensional motion now. It's not just constrained to the x-axis, not just constrained to the y-axis. It has a motion along both now. So typically, to begin a problem like this, what you need to focus on maybe first are the components of the motion, the components of the initial velocity. So you can tell from this figure here, there's definitely going to be a v0 y, and on this axis right here, there's definitely going to be a v0 x. There's going to be two components to its initial velocity, which you can find now. v0 x is going to be v0 times the cosine of that launch angle, and v0 y is going to be v0 times the sine of that launch angle. So there's two components of velocity now. And furthermore, when you sort of start getting ready for your analysis here, it's not always maybe reasonable or logical to expect it'll always work out this way, but if you start looking at the equations you have to describe how this motion moves, how this motion is going to work, if you look at this particular figure here, typically for these problems, the acceleration along the x-axis is going to be 0. In other words, as the object moves horizontally like this, there won't be any acceleration along the x-axis. Nothing is making the velocity speed up either in the left and right direction here. But as it moves here, you will have a single acceleration on a sub y will be negative 9.8 meters per second, or minus g. G is the gravity due to the Earth, and so as the object flies, say it's at a particular position right here, again, no x acceleration, but there will be a downwards g pulling it straight down like that with a magnitude of 9.8 meters per second squared. Excuse me, that's not quite right there. Meters per second squared over there. So given that, what do the physics equations look like then? Well, for the x then, you'll definitely have an x naught, and the v0x in this case here will just be the v0 times the cosine of theta, so there's your v0x times delta t. But because you don't have an x acceleration, the term that's normally here, the 1/2 ax delta t squared, that's just going to be gone because ax is equal to 0, so you won't have that. Likewise, v sub x here is just going to be vx naught, which is v naught times the cosine of theta. And normally you'd have an ax delta t here, but that whole term is going to be gone too. Again, these two terms are going to be gone in here for the simple fact that due to this type of motion, this type of two-dimensional motion, a sub x is equal to 0. So the equations that sort of drive this thing along the x-axis are this one right here and this one right here. These are your x-axis equations of motion for this type of motion. Let's look at the y-axis now, because there is an acceleration on the y-axis, so the equation will look a bit different. So if I look at the y now, well, I know we'll have y is equal to y naught. We'll definitely have that. And we have a v naught y, which is v naught times the sine of theta. Definitely have that in there, times delta t. But now, since a sub y is not 0, we will have the acceleration term in there, and the acceleration is downward, so we'll put a minus 1/2 g times delta t squared. This is the equation that governs the motion of the projectile along the y-axis here. It looks a little bit more complicated in the x again, because a sub y is not 0. Likewise, for v sub y, it'll be v naught y, which is now v naught times the sine of theta. There's your initial launch for the velocity in the y direction, and you'll have a minus g times delta t. So again, the vx does not have the acceleration term, the vy does, but there it is nonetheless. So these two equations down here will govern the motion along the y-axis, like this and like that. So there you go. So projectile motion, two-dimensional motion, in order to fully describe how the object is going to move, you have both coordinates acting together. You have x motion and you have y motion, and that's the defining characteristic. And if you sort of fish through the equations a bit, again, this initial launch condition over here involves an initial velocity and angle. How did that trickle its way into the analysis? Well, if you look down through the analysis, you see the launch condition all sprinkled through there. Here's that initial speed right there, v naught and v naught and v naught and v naught. And of course, the launch angle is going to have a lot to do with the subsequent motion, so there it is right in here. Here's a cosine of the launch angle. There's a cosine of the launch angle. Here's the sine of the launch angle and another sine of the launch angle. So all that's going to be in there. So that launch condition is very important for how the rest of the problem is going to come out. Again, the x equations do not have an acceleration term, so they're sort of absent in that regard, but the y equations do have an acceleration term. There's the g right there, and there's the g right there. And we are sort of assuming the sign convention by putting a minus sign in front of these terms here. The sign convention that sort of we're doing is that anything right is positive, left is negative, up is positive, and down is negative right there, just the way the Cartesian coordinate system is most familiar with. And so by saying that g is downwards, g is negative, so we're always going to have a negative term in front of these terms that involve the g. So that's sort of a nutshell how two-dimensional motion is going to work. Now, these equations, there's always going to be plenty of logic and maybe some other consideration that might have to happen to get these to work, but in a nutshell, that's how the launch condition for two-dimensional motion is going to manifest itself in terms of the equations of motion that we see. So once we have x and y, at any given time in the projectile's flight here, we can sort of figure out what x, y coordinates it currently exists at, say, to visualize where it's going to be. Likewise, we'll also know what its x and y components of velocity are going to be.